Okay, so hello everyone to my presentation on flowR, Programm Slicer for the R programming language. And first of all, you might find yourself with the question what a Programm Slicer actually is, and we will come to that. But first of all, a general question to the audience. Who in here has ever worked with R or is currently working with the R programming language in its everyday business? Okay, great. Okay, so for the others who maybe have never heard of R before, R is a statistical programming language, so it's mainly used in statistics and heavily used in research at that, for example, in the social sciences and in psychology in general. Whenever there's essentially a statistic to be calculated, people tend to use R. It's ranked 6th on the PyPy Programming Language Popularity Index, and there's a lot of packages available on CRAN for everyday use, which probably contribute to its popularity. And one important thing for R is that most of its user base is from non-computer science domain. So, of course, other programming languages like C++ or Python have people from non-computer science domains as well. But for R especially, it's more like that the vast bulk of the user base isn't from software engineering or computer science or everything, but from psychology, and so using R to achieve a singular purpose. And R in general, especially when it comes to research and whatever principles you want to uphold here, has a few problems. So, and we will come to them. First of all, R scripts usually don't replicate, and they have a problem with comprehension. So when you have your research script in practice, they usually do a lot of things, and we'll come to that just now. And so it's really hard to find out what another researcher did with his or her R script in practice. And last but not least, there's missing tool support, and we will investigate that as well. So there's not a sophisticated tooling infrastructure to essentially support researchers in achieving reproducible scripts and in getting the knowledge out there. And in general, there has been calls to introduce software engineering practices, replication, and other technology into the R ecosystem. So let's get started. We analyzed around 4,000 R scripts in the real world to essentially identify common and important problems, and one of them I'm showing to the left right now. It's probably way too small to see it. If you download the slides, you can essentially zoom, but I will zoom in as well so you can follow along. So, it's still very small. Anyway, you have to believe me then. In general, these R scripts are rather long, so around 300, 400 lines is the average in practice, and so there are ones going way over the 2,000 line mark. And all of these scripts we've analyzed here are essentially supplicants to publications, so they are reproducibility scripts attached to publications in peer-reviewed journals and conferences. So they are, in a way, at least to be assumed to be checked by other researchers. And now I want all of you to essentially assume the hat of another researcher who has to check or review or analyze the R script we have here, according to the claims made in the paper. And the first issue you may run into is that the script doesn't replicate, or even worse, it won't run. So most R scripts seen in the real world don't run, and there are several reasons for that. So first of all, what's really frequent in R scripts is that they include hard-coded paths, and if you're able to read it, you can see here that they'll use the set-read, the set working directory function, to essentially assume hard-coded paths for the files to lie in. And of course, you might think to yourself, now, okay, I can fix that easily. I'll just change the path to wherever the file lies now. But just for this file, there are, I think, 20 different locations of hard-coded paths, different locations which you have to adapt. And that's just one of the many issues that we have in the file. Another one, which is not so obvious at first, can be hopefully seen here, is essentially the usage of a randomness function, so for a random uniform distribution, and nowhere in the file they ever set a C. So even if you can get the file to run and the results differ from that shown to the paper, you have no idea if that is due to the randomness or if that's due to another issue within the publication. And so another study by Tritovic et al. Essentially showed that around 74% of R scripts as publications submitted alongside publications don't even execute completely. And now you might think to yourself, how can this happen? 74% is a really high number. But then again, you must think to yourself that R is an interpreted language and will only give you errors for a given line if you really execute it. So if you have your complete file interpreted from top to bottom and you may change something for a publication or anything, R will only issue an error if you try to re-execute the line. And if you don't, for whatever reason, then you have an error in your code and you may never know before anyone else tries to check. So there are a lot of problems. There are other problems as well. So if we then come back to the R script we have here and try to take a closer look at what it's actually doing, it's essentially creating 2 different models and generating 3 different figures for the complication. And that's, again, really common. And then again, you might see that there's a lot of other stuff up here. Anyway, up there you can see a lot of unlabeled segments, which are essentially helper functions, comments, initializations, and so on and so forth, which may relate to the rest or they don't. Now, if you are a researcher, either to check the R code or if you want to reuse a figure for your own work, you have the problem that whatever figure you pick, you have no idea which other parts of the code are relevant for that figure, and which you have to keep to replicate whatever they did. So, in general, it's really hard to comprehend because the figure generation below can depend on the figure generation above, or the model initialization can have a side effect that then affects the generation of the figure, or somewhere they load a package only if some other conditions apply, and then that package changes all the functions in the file. And so there are a lot of things that could happen, and in order to find out, you have to read essentially 400, 300, 700, or over 1,000 lines of code, and be able to understand these lines. So it's hard to understand for humans, but it's hard to understand for machines as well. So in general, R is interpreted, as I've said already, and it allows for a lot of interesting reflective capabilities. So first of all, we have the good old combination of eval and parse. Now you might think to yourself, well, Python has parse, JavaScript has parse, what's so worse about it? Or what's so bad about it? Well, in general, the problem with R is that it's used really frequently. And for really interesting cases, so I'm a software engineer, and what we can see here is essentially they concatenate the string with n underscore with period, which is essentially the gear where things happen, and underscore WC, so they concatenate a variable name, which they then parse and evaluate to essentially get the value of the respective variable, where a software engineer would probably tend to use a hash map or another data structure to get things ordered, but here it's done with reflective capabilities. And so an analyzer which does that has to understand what's happening in order to help programmers understand what code's really doing. You get another example, and both of them are from real-world code. The citations, again, are too small to see, but if you download the slides, you can check for yourself. It's here, and now that's, again, a lot of code, so I gray out the unimportant parts. What we can see here is a call to the body function in the last line, which essentially causes a modification of an existing function body to whatever you want. Here it's rather simple because it shows examples that can be followed on the slides, but you can imagine that it can grow much more complicated. And here we essentially use the substitute function to insert bins. It's assigned to up bins into this line in the upper function. So when that's executed, the function now reads like this, and when R tends to reinterpret these lines, it will do whatever the new code objective does. And so that, again, happens quite frequently, and it's hard for an analyzer to understand or track, or for any automated service to essentially help you and say, yeah, that part is important for that part. So last but not least, regarding the tool side, we have a lot of, but last but not least, we have several tools in the R ecosystem which try to help programmers write their code. First, we have RStudio, which is essentially the main thing that no one can get around when he or she tries to work with R, developed by Posit, which allows a lot of things, code highlighting. It has refactoring operations where it can rename variables or outsources parts to a function. Then there is the R language server, which essentially does the same things for the language server protocol, so it works with Visual Studio Code. It has a little different feature set, but essentially it provides the same things. And there are other R packages, like the linter package, which is essentially a linter like Sonar Source or whatever you are using for your research, which tries to bring up semantic or syntactic errors within the code. And there are other packages like code depends, which try to find dependencies in the code or even generate call graphs to help users understand what is going on. But then when you look closer at the existing tools, the problems are plenty. So just to sum that up rather briefly, none of them really look at the R code and try to analyze what's going on. All of them rely more or less on heuristics. So RStudio has a lot of heuristics. Sometimes they work, sometimes they don't. Then the R language server uses XPath expression. If you've never heard of XPath, it's essentially regex on XML trees, so it allows you to do some light pattern matching of tree structures. And similarly, linter, which uses roughly the same XPath expressions, and codepends package, which again relies on heuristics and only works on the top level. So all in all, the existing tool infrastructure is unable to help you with all of the problems that we've just mentioned. So we sum that up here, and I speed it up for time reasons. But all in all, we have a replication problem. We have a problem that a single R script is doing too much. We have the problem that it's not that easy to analyze R code for convenient existing algorithms, and that the existing tools aren't really sophisticated in helping programmers or researchers to do their work. And so, under the goal with better software, better research, the essential goal of flowR, or what we are doing, is currently focused on the doing too much part, but of course already trying to tackle the other problems as well, although we've just started building it, so we're open for any kind of feedback and support and whatever you have. So what is flowR doing? flowR is, as the title already mentioned, something called a program slicer. If you've never heard of program slicing before, it's essentially the technique of analyzing the program to reduce it to only the parts relevant to that affect a specific variable at a specific point. Or in other words, you have your code with a lot of figures, you're just interested in one figure, you mark that figure, and flowR then reduces the program for you to just the parts relevant for this figure. And they're again highlighted here. And what we now see in average in the real world is when we again recheck all of those 4,000 scripts, the average reduction in source code is around 70%. So the remaining source code is just around 30% of the original size. And then again, that's an average. So of course, there are good research scripts which do only one thing, where the reduction is not as effective and just some debugging statements are get removed. And then there are codes which do a lot of things. And here flowR can help a lot by essentially reducing and throwing away all the other parts for other generations. And so now the next question is, how is flowR doing that? What we're essentially doing is a multi-stage pipeline where each step can theoretically be reused by other researchers for whatever they can use it for. So we start by parsing the R code. That's slightly compiler here. So we get an AST or a syntax tree, which we then normalize to generate the data flow. And if you never heard about data flows or what they're doing before, it's essentially just you have variables in your code and you have definitions which define values for these variables, and the data flow graph tells you this variable refers to this or this definition, depending on the condition of this, whatever, if conditional, what you're using. And so we have a big graph. And then what we can essentially do is we calculate the slice on that graph as a reachability problem and reduce the program to whatever is necessary for you to then calculate what's then called the slice. And flowR in its current stage is already split up. So if you're now thinking to yourself, hey, I want to write better linter rules for the R programming language to, for example, check null errors or uninitialized errors, or to help improve reusability, then what you can currently do is just use the data flow graph as produced by flowR to essentially enhance reusability. And so now how to get flowR? So what we currently have for you to check out flowR right now is we have a Visual Studio Code extension where you can essentially just open your R, it's located here, where you can just open your R code up in Visual Studio Code, select whatever variable interests you, and get the slides so that you can just check it out. What we have is two nodes, and then again, I think the beamer isn't showing that perfectly, but now the unimportant lines are grayed out, and there are two nodes where you can just reduce it to the program that's important. And for other people, probably those which are more akin to programming, there are other interfaces you can use to essentially use flowR right now in your tooling. We have a server endpoint that can be used to essentially query flowR with arbitrary R code. We have library usage, so if you want to, you can integrate flowR into other programming languages to call it directly from your code. And there's a REPL to play around with, so if you've never heard of it, it's essentially a command line, a way to interactively probe what flowR is saying about different pieces of the object. So then again, here we are. It's Dockerized, so if you want to, you can check out the REPL right now. And in the end, where we are is flowR is the approach or the first try to essentially improve on the problems I've shown you in the beginning. It just started. So I'm open for any kind of feedback, suggestions, whatever you have. If you're interested, I'm happy to get in touch. And so, yeah, welcome any kind of questions. Thank you.